All right, so what I want to do is demonstrate a couple of things so you know how they work. So this is the fire syringe. The blue piece here is a screw on, so you're going to have to unscrew it. And then you're going to take a little piece of cotton and put it in the bottom. It works best if you just use a very small amount. You don't want anything very big at all. So I tried to give you just a tiny amount in the bag, but you maybe even want to like tear that in half. You're going to push it down to the bottom. Try not to compress it because you want it to be fluffy. So you can there should be some pipettes floating around that you can push it down with, but you just want to get it to the bottom. You don't want to squash it. You're going to stick this in so that it stands on its own and then screw this back into place. And then what you want to do is have this on a surface like the table. You're not going to hold it in your hand. I'm going to hold it in my hand to demonstrate. But it will work better if you have it on the table. It might even work better if you have somebody else hold the bottom steady while you're doing this. The person who is observing is not going to be the person who's pressing the plunger because you can't do both at the same time. You really want to slam this down as hard as you can. So we're not going to do a slow press. We're not going to do up and down like this. We're going to do one really hard slam. Okay. You should see evidence of fire. In some cases, we actually saw flames. In some cases, we just saw smoke. So at the very least, you should see smoke. That's what you're looking for with this one. This one on your individual sheet is technically the only one that we will have three things that are not held constant because we can't really hold the volume constant. We're going to, for the idea of comparing pressure and temperature, we're going to pretend like we're holding the volume constant, but technically the only thing that's constant is the moles. So that would be the only one that you would circle as being held constant.
Yeah.
So there are two styles of these. So we have this is the bell jar, and then we have the bottom part. And this just rests on here. There's no screw, there's no seal, it doesn't slide in. So they're loosely held together. Some of them, there is a hole in the side here where you're going to pull the air out of. Some of them, that hole is in the top. So the attachment will work differently, but you'll know by where the hole is. You're going to have a syringe with some tubing on it. This has a valve here and here. So the valve only works in one direction. So the longer end is going to get attached to the bell jar. And so in this case, I just push it in. For the ones that attach on top, you'll have to screw it in place. So when I pull out the air from the syringe, it's going to go through this valve out, but it can't go back in. Okay. And then when I push the syringe back in, it can go out the valve in this direction, but it can't go back in. So that's how that's going to work. So I'm going to do a little demonstration here. So we got a marshmallow peep in here. This guy's made of marshmallow. And we're going to see what happens when we reduce the pressure in bell jar. There you go.
I think that's about as big as he's gonna
Yeah, it's probably as big as he's gonna go.
Holy.
And then when you let go, it turns back down. Okay, so the moles in theory is going to be held constant because all the air in theory is staying inside the marshmallow. We know a little bit is changing. Did the temperature change? No, solid room temperature. But we changed the pressure by reducing the air pressure inside the jar, and then we changed the volume, obviously, of the sky. All right, so then it tells you to put a couple other things in there, including the ping pong ball. So I'm gonna leave this here so that they can see steps.
There's a lot there. Yeah. Okay, I think he's had enough. That's my fault. You think? Well, yeah, so we're doing a lot. Like that. I mean, yeah, it's not a thing happened.
This is kind of a new one I'm trying this year. You have a soda bottle with this thing that's called a fizz keeper. So they sell this so that you can screw this on the top of your bottle and then pump your bottle with air. And that is supposed to keep the fizz in your soda. And we'll talk next week why that doesn't really work as well as they might indicate. But what we're going to do is we're going to put some miniature marshmallows in here and use this to increase the pressure inside the jar. So we're going to assume that the marshmallows have all the air contained in them, and that's going to be pretty constant, that they have the bubbles are sealed, and so the air isn't getting out, and we're going to increase the pressure. This is the one that doesn't work as well as the others because these things are a little bit old, but the two toppers that I have out there, people in the last couple of classes were able to make them work pretty well. What I will say is that if you get this really high pressure, when you take it off, it can fly out of your hands. So when you unscrew this, you should be wearing goggles. Okay, and I'll put goggles on tables for that. Okay, so this is part 4 of the modeling gas laws. And we have here a bottle with a topper here that is called a fizz keeper. So this is a pump that pushes air from the outside into the bottle. And so as I do this, you can watch what happens to the marshmallows. It will be pretty subtle. But after I've got it nice and full, I'll hold this still so you can see what's going on. All right, it's starting to leak, but you might be able to see that the marshmallows are just a little dented and a little bit smaller. I'm going to try pumping it up a little bit more and seeing if I can get the camera to focus a little bit better. Let's see. Okay, so at this point, you should be able to tell that the marshmallows are a little bit smaller. And if you could see a little bit more clearly, you would be able to see that they are dented just a little bit. And hopefully you'll be able to notice the change as I let the air in. They will grow slightly. So you might have noticed that. All right, so that's. I want you to take a look up here. One of your questions asks you, it gives you a picture of the bell jar and asks you what it would look like afterwards. I sometimes ask this on quizzes and tests, so this is a good one to know how to attack. So we're looking at 3 different things here. We want to know what happens to the size of the marshmallow, and then we want to know what happens to the particles of the air inside and outside the marshmallow. So I've done a balloon instead of a marshmallow, easier conceptually. Okay, so ahead of time, we've got this balloon. I've got 3 particles of air. Obviously, there's a lot more, but we're just going to think proportionally. And then I've got 10 dots outside representing the particles of air. So if I look afterwards, what happened to the balloon itself or the marshmallow itself? It increased in size. So some of you were able to get the peak to pretty much fill the whole thing, right? So I would draw a bigger balloon. All right. What about the air particles inside the balloon? Are there more, less, or the same number? Did we put any air into the balloon? No. Okay. So it's the same number. We have a boundary all the way around. It's sealed. So it's not getting bigger because we're putting more air in there. What's happening to the particles then, if it's the same number?
Particles on the outside are decreasing.
That's true, but I'm inside the balloon. What's happening to those particles? Are they changing size? No, because air particles are just going to stay air particles. What about the distance between them? More distance between them. So instead of them being real close together, I would draw them spread further out. Okay. So then, Ashley, you were saying that on the outside of the balloon, we would have fewer particles because as we pull that syringe, we're actually decreasing the air in there, and the air is the particles of gas. So instead of drawing 10 dots, I might draw just 4 or 5 dots, showing that there's less air on the outside. So why does it change size? It's not that the inside of the balloon is pushing harder, it's that the outside air is not pushing nearly as much on the balloon. And so, but when the inside air collides with the flexible boundary of the balloon, it expands. Okay, so remember, if we have a flexible boundary, the pressures are going to try and equalize. And that means that the lower pressure is going to try and expand the gas, and the higher pressure will have less room. And so it will end up having less volume for those particles. Okay, so in contrast, when we have our soda bottle, put this over here, and it's not a great drawing of a soda bottle, but we've got a marshmallow down here, and we've got some air in there. And instead of pulling the air out, we're trying to put the air in. So what happens to the marshmallow itself?
Condenses.
It condenses. Now, some of you were able to see it actually shrink, but in most cases, it just looked a little dented. So instead of, nice and round on all sides, maybe it had a dent in the top, or the sides were going in a little bit smaller. But you could see it getting a different shape, and hopefully you saw that it was getting a different size. So did the number of air particles in the marshmallow change? No, I haven't drawn them because it's small, but no, they didn't change. What about in the bottle? Did I change the number of air particles in the bottle? Yes, because I was pumping in air from the outside. So if I were drawing this one, I might, instead of 7 dots, do, 10 or 20 or something. So I have a lot more air in there. Okay. So I want you to think about where those air particles are. Remember that pressure is related to collisions. So more particles means I'm going to have more collisions, and that's going to be increased pressure. And in case of the vacuum jar, fewer particles is going to be fewer collisions. And so that lowers the pressure. Okay. Do you have questions about any of the other experiments? Okay. So on your individual sheet at the bottom, it asks you to identify the combined gas law and the ideal gas law. Which one is this? PV equal nRT. That's the ideal. And which one's this? Combined. So the combined gas law, what restrictions do we have on the units that we're allowed to use for the combined gas law?
You just have to have the same units on both sides.
Mostly just to have the same units on both sides, but there's one particular unit we have to do. What's that one? If I have something, Kelvin, yeah, if I'm doing something at 0 degrees Celsius and I plug in a 0 here, then I'm gonna get my calculator mad. I have to use something that doesn't have negatives. So that's absolute scale is Kelvin. Okay, so must use Kelvin here. And in fact, that's true over here as well. So this has to be Kelvin as well. Okay, but because R has units, R is equal to 0.08206 liters atmospheres per mole Kelvin. What units do I have to use for pressure? Atmospheres. So even though it's easier to actually physically measure the pressure using a barometer with millimeters of mercury or torr, I need to convert it to atmospheres to use this equation. What about volume? Liters. And then moles is just moles. So remember, N is how many moles of the gas we have. And then again, temperature has to be in Kelvin. Okay. All right, so I want to go through an example of using the ideal gas law. This is somewhat similar to what you're doing in lab next week. So hopefully that will be helpful for you. I have written on the chalkboard here a description of an experiment. Suppose you are heating 1 gram of potassium chlorate. And you are going to produce oxygen gas. So this is the equation of how that works. So we have potassium and chlorate. Chlorate is ClO3. And so it's going to produce potassium chloride and oxygen. We don't care about the potassium chloride right now. Now in lab, that's actually what you're going to be solving for. But for our purposes, we don't care about that. So we have our oxygen over here. So then we have the measurements about it. The gas is collected over water at 21.2 degrees Celsius, and the pressure is equalized with the room pressure. Now, remember I told you the other day that when we capture the gas over water, that technically inside the eudiometer or wherever we're collecting it, that's going to be a different pressure than the room unless we make those water levels equal. But it's really hard to get the eudiometer, which is nice and long, at the same level as the water in your dish. So what we used to do is like move everything over to a big bucket of water. But then people would spill things and yeah, it just didn't really help us a whole lot. So we're just kind of skipping that. But technically you would need to equalize the pressure. And then we read the barometer, and that's 741.5 millimeters of mercury or torr. And we're going to try and find the volume of O2. So this is actually not just an ideal gas law problem. This is also a stoichiometry problem because it's asking about one chemical, but it gave us information about a different chemical. Okay. So the first thing that we need to do is we need to figure out how much of that potassium chlorate we have. So we're given grams. How are we going to go from grams to moles? Divide by the molar mass. So since you're so smart, why don't you calculate the potassium chlorate's molar mass for us? And we'll come back to that. Now, normally I start with the amount of a particular item, and then I do that whole fraction thing where I multiply that by the fractions. In the case of the ideal gas law, we have so many variables and they're on both sides of the equation. I really like to work with just what are those variables first. So the pressure is 741.5 torr or millimeters of mercury. Can I leave it like that? No. Ideal gas law says I have to go to atmospheres. So what do I have to do to get to atmospheres? What number am I going to use? 760. So I've got two choices. I can either divide by 760 or multiply by 760. What do you think? Divide. So that's going to get us somewhere close to 1.
Now we have 4 sig figs on our, conversion here. All right, I'm gonna have somebody at this table calculate this for me, 741.5 divided by 760. While we're doing that, I'm going to look at volume. So the volume was, we don't have a volume. That's what the question is about. So what I like to do is put a question mark there so I know that's the thing that I need to solve for. Then I'm gonna have my temperature, and the temperature was 21.2. Can I leave it as 21.2? No, it's gotta be in Kelvin. How do I get to Kelvin? 273 point, some people add 1, some people add 2. We'll see in this case, it's not actually going to matter, but we can do 2. Oops. And so that should give us 294.4 Kelvin. Okay, this table, what was the pressure in atmospheres?
0.9756.
0.9756 atmospheres. Okay, and then R is a constant, so we're just gonna plug that in. And the last piece that we have is moles, but we haven't been given moles. So that's where we're gonna use the grams to get us there. Okay. 1 gram of potassium chlorate. And then actually found our mass. 122.548. Could you be so kind as to take 1 gram and divide it by that number?
00816.
All right, and so our original number only had 3 sig figs, so we're only reporting 3 sig figs here. Now, we found moles, but what did we find moles of? The potassium chlorate. Is that a gas? No. So that's not what we're going to plug in. This is what makes it stoichiometry. So we're going to say, so this was step 1, find moles. Step 2, we're going to convert to what we want. 1,6. So what we have goes on the bottom, KClO3. What do we want? Oxygen. That's the one that's the gas. And what numbers am I going to plug in there? Where am I going to look? The balanced chemical equation. So I'm going to tilt this back up here for those of you at home so you can see that balanced chemical equation. So for the potassium chlorate on the bottom, I'm going to pull the 2. For the oxygen, I'm going to pull the 3. Okay. All right. So actually, since you probably still have that 0.00816 in there, can you multiply that by 3 and divide by 2 for me?
01224.
Okay, and this is moles of oxygen. And since I only had 3 sig figs on the potassium chlorate, I'm going to just round that to 0.122 here. Now I'm ready to plug things into my ideal gas law. I'm going to rush through this really quick. We'll try and get it in 30 seconds. The ideal gas law, I would rearrange it before you start plugging things in. I want V, so I'm going to divide both sides by the P. So I can just have V is equal to nRT over P. And then I'm going to plug it in, 0.122, 0122 moles, 0.08206. That's R. That will always be given to you. You don't have to memorize it. Our temperature, 294.4. And our pressure, 0.9756 atm.
And Ashley, can you plug that in for us?
0.302.
I'm gonna write this up here so it's easier to see. 0.302 liters. Okay, the last class got 3.02, so somebody missed a factor of 10 at some point. I'm not sure whether it's this class or the last class. So that can be to you to plug in at home and see whether this is right or whether we need to move the decimal. Okay, so do your prepare to learn over the weekend. Any questions? Okay,